All right, today we got logs. We're going to be talking about logarithms and why they are useful. And today's kind of more of a basic overview of them. But let's talk about why we need logs first to solve problems here. So, you were born and your parents put $1,000 in a savings account at 3% interest, compound monthly. And how many years will you have? 12,000. Write the equation that models the situation. So, anyways, in this case here, since you start out with 1,000, that's going to be the thing that goes out in front of the parentheses. I'm using that formula that we learned the other day. You put your principal out in front, you go 1 plus the interest rate, or 0.03, and then you're going to divide that by the number of times you compound per year, which was monthly. So we'll put 12 down here, and then we'll raise this all to 12 times the time. And the issue here with this is we don't know how much time is going to pass, but we know our final amount is going to be this amount right here, this $12,000 right here. And so the whole idea is we use logs eventually to solve for exponents. We don't really have a way to do that at the moment right now. So that's why we're going to be learning about logs here over the next few days here. So today we just talk about how to write something in log form, and then we're going to simplify a few things. Over the next few days we'll graph, and then we'll also solve equations that look like these here. So that's kind of the why behind it. So let's look at an exponential equation. We've seen these over the past few days. You usually have some type of number, and if you have an exponential thing going on, you have a base, and then P stands for the power. So you have a base, power, and a number. Now when you write something that's in logarithmic form, notice here you got log, and then they put the b right there. They're going to write the b kind of small like that, and we call that, I guess like a little subscript, I guess, right there. So log base b of a number, and then equals the power right there. So logs essentially are, in a way, logs are equal to the exponents. Okay, and then let's talk about how to switch up the forms here. So notice over here we have 36, that's the number, I guess, and then equals 6 raised to 2. Okay, in log form, since the base was 6, the thing that was being raised right there, we put a little 6 right there. So log base 6, and then you put the number right there, 36, and then equals 2. So we're saying 2 is the exponent of that situation, basically. All right, and what I like to do to help myself here is I draw these little arrows. To switch forms, you start with 6, you go towards the equal sign to 36, and then you say 2 is the next number right there. So kind of like what I was saying here. So this is log base 6, that's the first number right there. And then you say of 36, that's the second number, and then usually it equals a number, so you'd say it equals 2, kind of like that right there. And notice that's just the same exact thing that we have right here in the other order. And then if you have it in log form, you can go the other way here. So you're going to start here, 6. You always start with the base, no matter what. You go towards the equal sign, so 6, and then to 2, and then equals 36. 6 to 2, and then equals 36. And that's a little way, just a visual way, I guess, to switch the different forms around right there. Some people, I've heard other teachers call this like the little scorpion, kind of like a scorpion tail. It's not one to write here, so that's something you can call it there if that helps you figure out how to switch the forms there. So we're actually going to try it out here on this next one. So notice the order is a little bit different. So you always start with the base and you go towards the equal sign. So you do that. So you go from 4, you go to 3. So we're going to say 4 to the third, and then equals 64 right there, which is actually a true statement. So 4 cubed equals 64. All right, let's try one going from exponential to log. So once again, always start with the base. 2 is being raised to something, so that's the base. Go towards the equal sign. 2, 64, and then 6 right there. So we're going to say log base 2 of 64, and then apparently equals 6. Okay, so So there you go. I guess we'll write that over here. Okay, let's try the next one here. Start with your base always. So that would be 12 raised to 1 equals 12. So 12 raised to 1 equals 12. Okay, this one's kind of weird because you got a fraction and a negative exponent here. So here's your base. So we're going to say log base 1/4 of 4 equals -1. So log base 1/4 of 12, or what was it, of 4 equals -1. And that is how you switch between your forms right there. So it takes a little practice. It's weird at first, but if you draw that little arrow, I think that'll really help you keep everything organized. All right, so some of these, the first examples that we're going to be starting out with here are examples where we evaluate a log without a calculator. Now we can type all this into the calculator. I'll in fact show you here in a second how to do that, but most of these are going to be expected to do without a calculator. So what I like to do on these first here is actually set it equal to a variable. I'm just going to call it x for right now. And then what I'm going to do is I'm going to switch forms. I'm going to say 5 and then raised to x equals 625. Okay, and then I got to think about the exponent that makes true right there. So like if I had like x is 1, 5 to the first power is not 625. That'd be too small, right? Or 5 squared, that'd be 25. That would not be 625. So that's a little too small. If I did 5 to the third power, that'd be 125. So actually this one here will be 5 to the fourth power right there. So we're going to say x is equal to 4, or you can go and say that this thing simplifies down to 4. 4 is what that simplifies to. All right. Now, if you want to check with your graphing calculator, especially when you're just learning these here, I'll show you how to do it here in the graphing calculator. So I'm going to pull this down for a second. And then to do a log, there's a log button here, but it doesn't put the base in right there. So to get the log with the base, we're going to hit math. And then I think we scroll down a little bit here. I think it's 0. So we'll click down until we get there. Nope, there it is. Okay, so it's A right there. So this is log base, and then you put your number there. All right, so log base, so we'll put in 5, I guess. And then I guess it was of 625. And then we'll hit enter, and notice that simplified to the same thing, 4. So that's a way you can go and check your work here on these. So let's go ahead and continue with the next one here. So I think this one will be a little bit easier. So once again, set it equal to x, switch forms. So I'm going to go 11, always go towards the equal sign. 11 raised to x equals 121. Okay, so in this case here, x, like if I'm doing 11 raised to something, x would have to be 2 in this case. 11 squared would equal 121. So we'll say that this whole thing simplifies down to 2. Okay. Now sometimes you'll get these examples right here. This one's going to be a little bit tricky here, so I put a star next to it. So this one is saying 36 raised to x equals 6. Okay, now something like this right here, you're basically asking yourself, what do I need to raise 36 to get 6 right here, a smaller number? Okay, so if you think back a few units ago, or even, yeah, I think that was maybe a unit ago here, we were talking about square roots and cube roots a lot. So if I could do somehow a square root, we could get to 6 right here. And a square root, we learned the other day that you write a square root, you can also write it as raised to a fraction right here. So actually x in this case is going to be the fraction 1/2. If I do 36 raised to 1/2, that's the same exact thing as doing a square root, and the square root of 36 is 6. And that'll be the answer there. And you'll have to do a few examples there to really, I guess, nail that down here. So, you know, if you want to add in an extra example, I could do something like this. I could go, I don't know, like log of 81, and then log base 81 of 3. So let's try this one out here. So I guess I'll call this D, if you want this here. So I could say 81 raised to x equals 3. So what type of root would I need to do of 81 to get 3 right there? And we could do a square root. A square root won't get us down to 3. We could do a cube root. Actually, couldn't do a cube root. There's not a perfect cube, but you could do what we call a fourth root right here. So a fourth root, like this right here, of 81 would be 3. And the way we write a fourth root, we write that as a fraction 1/4. So just be on the lookout there for those. Every now and then you'll get, some tricky ones kind of like that. So, okay, probably one extra example I do want you guys to add, I think this shows up in the homework, is when you raise something and you get a fraction. So like, for example, we could do like log, let me make sure I'm kind of coming up with this on the fly here. So let's say like log base 2 of the fraction, I'm trying to come up with something. Okay, of the fraction, let's say 1/16 right there, 1/16, and then figure out what that simplifies to. So go ahead and add this here. We'll call this example E right here. So we'll set it equal to x. We'll do 2 raised to x equals 1/16 right here. All right, so to generate a fraction from an exponent, we learned the other day, if you do negative exponents, like for example, if you had like 3 raised to -1, that makes the fraction 1/3 raised to the positive 1. Or if you had like 3 raised to -2, you could say that's 1/3 to the positive 2 right there. So that would make a bunch of fractions. So in this case right here, I would need x to be a negative number and think, all right, to get to 2 to 16, I'd need to raise it to the fourth. To make it a fraction, you'd make it a -1/4. Or negative, I'm sorry, not a -1/4, a -4 right there. So if I go off to the side, I can go test it out. 2 raised to -4 is 1/2 to the positive fourth, which is 1/16. So every now and then you get these weird ones where you'll get negative exponents right there. So I would add in those 2 extra examples, and that should cover all the different homework type of questions, I guess. Okay, now you have 2 special types of logs here. We have a common log, which is a log of base 10. So it looks something like this. You could say like log of like 27 or something like that. This would be implied of a base 10 right here if it's not written. Okay, and then you guys also have natural log, and natural log is when a base is e, and then we usually use ln for natural log. I'm not sure why it's not nl instead of ln, but that's, I guess, what they decided. So if you had something like this, like ln of like 18 or something like that, it would look like this, and then there'd be an implied base of e. That'll be significant, especially a little bit later on. So evaluate using your calculator. So 2 ways you can approach this type of problem here. So since this is a common log right here, it's a log, it's implied base 10 right here. Since it's a common log, we can actually just take our calculators, and then we can hit the log button right here, log of 9, and then enter, and then it gives you that decimal right there. So we'll write that here. That was 0.9, how many decimal places? 3. So 0.954. And that would be, the approximation for that log right there. Now you could get real fancy if you wanted to go take your graphing calculator and do the math button and then scroll all the way down to A and then put in the 10. You can, but obviously it takes a little bit longer. But notice you'll get the same exact decimal on those on those common logs. So anyways, that's that here. I'm going to just kind of speed through the rest of these here real quick. My calculator off the screen. So if you do log base 10 is 732, you're going to get 2.86 and then 5 once you round up. If you go log of 0.85 for this next one, looks like you get a negative number, so you'll get negative 0.07, I guess 1 once you round. And then natural log, remember it's implied to be a base e, but there's actually a natural log button on your calculator. if you look right here, it's over here on the left side, natural log. So anyways, natural log of 22 gets us the decimal 3.091. Those would be your different evaluations for those. Alright, now there's a couple of properties that we're going to learn here today using logs, and I'm going to explain them by setting these different things here equal, I guess, to x, and then see if we can kind of come up with an idea. And then after we're done, we'll just kind of go through what you need to know here for these. But let's say you have log base b of 1, and you're trying to figure out what that simplifies to. So I'm going to just call this x for just a second, or whatever variable you want to call it. So if I switch forms, I'm going to write this as b raised to x equals 1. So I'm saying b can be any number you want. So if I take a number, raise it to something, and get 1, the only number that would work for that is if the exponent was 0 in this case. So a simplified version of this here, we're going to say the log of 1, I don't care what the base is, the log of 1 is 0. You can actually test that with your graphing calculator. If you just hit log or even natural log of 1, that'll get you 0. Okay, so that's the first property. Second one here, it's kind of like the same thing here. We're going to say b raised to x. So b raised to what gets us b right here. And if you almost think about it here, saying b raised to what number gets you just regular b. The only thing that could happen right there is if b was 1. So if you had like a power of 1, that's the implied power right there. So we're going to say that this thing here, the log base b of the same number b, whatever that is, we're going to say is 1. So like, for example, if you want to write off to the side, if you had like log of like base 8 of 8, sometimes they put it in parentheses like that, that will simplify down to 1 right there when they're the same. It's like they, in a way, cancel each other out. Sorry. Alright, this next one, kind of the same idea, except they already used the variable x right there. I guess x can be anything, so I'm going to put y over here. So I'm going to say b raised to y equals this entire thing right here. So I'm going to say b raised to y apparently equals b raised to x. And then what some of y'all might be able to clearly see here is that means y is equal to x, which means I can replace this y right here. I'm going to put an x right there. Okay, and what that really means is these logs essentially cancel each other out, and then whatever the exponent is here, that's going to be the leftover thing. For example, one that actually has numbers, if I had like log base 2 of 2 cubed, this would simplify down to 3. It's like the 2 and the log base 2 cancel out, and you're left with just that exponent. That's all that is saying there. Okay, and then the last one, this one's kind of a weird one here. So this one's actually in exponential form here. You have b raised to this log right here. So it's a little strange here. So what we're going to do here in this case is rewrite this in log form. So we're going to go and take, oh, this thing is kind of being slow here. So I guess just listen for a second. I'm not sure why it's not updating. Here, bear with me for a second. There we go. Now it's updating. All right. If we do b raised to y right there, we're going to say the log base b of y equals all of this stuff here, which apparently is log base b of x. And since you have the logs on both sides, you can essentially say that the y is equal to x. Whatever y is, it's got to be the same. So what does that mean in this situation? I'm going to replace that y with an x, and we're basically saying the exponent and the log base b right there, those are going to cancel each other out, and then you're left with x. And here's something that might look like that. If you have, I don't know, like 9 raised to log base 9 of 2 or something like that, this will simplify down to 2. Those will cancel out. So anyways, do you need to know the setup of these? Not necessarily, but I did want to show you that. But you do need to know these properties here. The log of 1 is always 0. The log base b of the same base right there will always be 1. And then kind of an extension of that, whatever the exponent of the log base b of b is right there is going to be simplified down to just the exponent. So the logs cancel out, and then you can also say the base and the log base will cancel out. And we'll use those ideas here on this next page, or this next section. So let's try it out here. Now, first of all, this one's kind of weird because it looks like this fourth option right here, except they didn't write the power, or I'm sorry, they didn't write the base of this little log up here. So this is actually a common log. It's implied to be 10 right there. So we're going to say the log base 10 of 10 right there, that those are going to cancel, and then this just simplifies to 4. Okay, so if you know that property, that's going to speed you up. Now, with this next one here, if this 25 right here, if that was 5 right there, we could just say, oh, those cancel out. And the issue is it's not 25, or I'm sorry, it's not 5, it's 25. So what we're going to do here is I'm going to rewrite 25. I can rewrite that. 25 is actually the same thing as 5 squared. So I'm going to rewrite this as 5 squared, and then with that x up there in the exponent right there. And then we're going to say that both of these right here, log base 5 of 5, that cancels out, and this thing will simplify down to 2x right there. And I put a star next to that. You see a lot of those types of problems. So replace that 25 with what 25 it can be written as far as, a base and an exponent. So we rewrote 25 as 5 raised to 2. And that made it to where we could simplify. Okay, I think this next one, pretty much the same idea. So can we rewrite 27 with a base 3? Can I write 27 as 3 raised to something I can? That'd be 3 cubed. So I'm going to write log base 3 of 3 cubed. All right, so the log base 3 and then the number of 3, those will cancel out, so this simplifies down all the way to 3. And you'll be expected to do these without a graphing calculator, so you'll need to practice it. So you can check with the graphing calculator, but you'll need to practice that. Okay. All right. Next, after this here, we just got to find the inverse functions. I think the next day we're going to be doing a lot of graphing, so it'll be really helpful to find the inverse. So to find the inverse of a function, usually you switch x and y, and then solve for y. So we're about to learn here that logs and exponential equations, these are going to be inverses of each other. So here's how you're going to take a log equation and then rewrite it in exponential form to find the inverse. So first of all, switch your x and y. And then now we're going to switch forms on these. To find the inverse of a log equation, you got to switch form. Take your base, go towards the equal sign. 4 raised to x equals y. 4 raised to x equals y. And then I'm going to get my proper notation. I'm going to say that's the y inverse. That's the inverse equation right there. And then also, if you want to get real fancy and do your f inverse, you can say f inverse of x is 4 raised to x right there. So 2 different ways you can write it. That is it there on those. Sometimes they might give you a little bit more action. So like this one here, we'll say x equals log base 3 of, I guess, y plus 2. And then we're going to switch forms. So I'm going to take 3 right there. I'm going to do 3 raised to x equals all of this stuff. This y plus 2 is kind of like a package deal since it's got parentheses. So 3 raised to x equals y plus 2. And then finish getting y by itself by subtracting 2 from both sides. And the way we write that, we're just going to write 3 raised to x and then minus 2. Make sure to emphasize that it's not in the exponent there. Some people don't do a really good job of rewriting this here. So that's what I would do right there. 3 raised to x and then minus 2, not in the exponent there. Okay. And then I think we got one more here. Let's see what's going on with this one here. So we'll go, I guess, x equals log base 3 of 6y. Switch your x and y. All right, take your base, whatever it is, base 3. 3 raised to x, go towards the equal sign, and then equals 6y right there. And the 6y, those kind of go together. If you want to throw parentheses around it, there's implied parentheses there. So once again, 3 raised to x equals, 6y. All right, and this one's actually kind of tricky here because a lot of people are going to say divide by 6, and then they're going to think that reduces to 1/2, which it doesn't actually. So 2 ways you can write this. It's just 3 raised to x over 6. Technically, whatever the exponent is, you have to raise it first before you divide, and that's why you can't reduce. And then another way you can actually write this is 1/6, and then times 3, and then raised to x, kind of like that right there. And really, like I was saying, the 3 raised to x technically comes first. So there you go. There's your inverse equations. And that is it for today.